Of course, if f depends on more variables, then you just have, you just have more terms in here. Okay, here's another thing that may be a little bit confusing. So what is tempting? Well, what's tempting here would be to simplify these formulas by, removing these partial x's. So let's simplify by partial x. Let's simplify by partial y. We get partial f partial u equals partial f partial u plus partial f partial u. Something is not working properly. Okay? So why doesn't it work? Well, the answer is precisely because these are partial derivatives. These are not total derivatives. And so you cannot simplify them in that way. And that's actually the reason why we use this curly d rather than a straight d. It's to remind us, beware, there's these simplifications that we can do with straight d's that are not legal here. So somehow when you have a partial derivative, you must resist the urge of simplifying things. Okay, so no simplifications in here. That's the simplest formula you can get. Okay, any questions at this point? No? Yes? So when would you use this, and what does it describe? Well, it's basically when you have a function given in terms of a certain set of variables, because maybe there's a simple expression in terms of those variables. But ultimately, what you care about is not those variables, x and y, but another set of variables, here, u and v. So x and y are giving you, a nice formula for f, but actually the relevant variables for your problem are u and v. And you know how x and y are related to u and v. So of course, what you could do is you could plug the formulas, the way that we did substituting, but maybe that will give you very complicated expressions. And maybe it's actually easier to just work with the derivatives. So the important claim here is basically we don't need to know the actual formulas. All we need to know is the rates of changes. If we know all these rates of change, then we know how to take these derivatives without actually having to plug in values. Yes? Yes, you could certainly do the same things in terms of t. If x and y were functions of t instead of being functions of u and v, then it would be the same thing. And you would have the same formulas that I had, over there. I still have it. So why does that one have straight d's? Well, the answer is I could put curly d's if I wanted. But I end up with a function of a single variable. So if you have a single variable, then the partial with respect to that variable is the same thing as the usual derivative. So we don't actually need to worry about curly in that case. Okay, but that one is indeed, it's a special case of this one, where instead of x and y depending on two variables u and v, they depend on a single variable t. Now, of course, whether you call your variables, any name you want, it doesn't matter. But so this is just a slight generalization of that. Well, not quite, because here I also had a z. See, I'm trying to just confuse you by giving you functions that depend on various numbers of variables. If you have a function of 30 variables, things work the same way, just they're longer, and you're going to run out of letters in the alphabet before the end. Okay. Any other questions? No? Yes? What? Oh. Yes?
If u and v were both depending on another variable, what would that look like?
So if u and v themselves depend on another variable, then you would, continue with your chain rules. Maybe you would know how to express partial x partial u in terms using that chain rule. So if u and v depended on yet another variable, then you could get the derivative with respect to that using first the chain rule to pass from uv to that new variable. And then you would plug in these formulas for the partials of f with respect to u and v. So in fact, if you have several substitutions to do, you can always arrange to use one chain rule at a time. You just have to, do them in sequence. So that's why we don't actually learn that, but you can just do it by repeating the process. Probably at that stage, the easiest to not get confused actually is to manipulate differentials, because that's probably easier. Yes? So curly f does not exist. That's easy. Okay? Curly f makes no sense. By itself, it doesn't exist alone. What exists is only curly f curly d f over curly d some variable. And then that accounts only for the rate of change with respect to that variable, leaving the others fixed. While straight df is somehow a total variation of f. And so it accounts for all of the partial derivatives and their combined effects. Okay. Any more questions? No? Okay, so let me just finish very quickly by telling you again, one example where concretely you might want to do this is you have a function that you want to switch between rectangular and polar coordinates. So just to make things a little bit more concrete, so if you have polar coordinates, that means that, in the plane, instead of using coordinates x and y, you will use coordinates r, distance to the origin, and theta, the angle from the x-axis. So the change of variables for that is x equals r cosine theta, and y equals r sine theta. And so that means, well, if you have a function f that depends on x and y, then in fact you can plug these and get a function of r and theta. And then you can ask yourself, well, what is partial f over partial r? And that's going to be, well, you want to take partial f, partial x, partial r, plus partial f, partial y, partial r. And so that will end up being actually f sub x times cosine theta plus f sub y times sine theta. And you can do the same thing to find partial f, partial theta. And so you can express derivatives either in terms of x, y, or in terms of r and theta with simple relations between them. And and one last thing I should say. So on Thursday, we'll learn about more tricks we can play with variations of functions. And one that's important, because you need to know it actually to do the p-set, is the gradient vector. So the gradient vector it's simply a vector. So you use this downward pointing triangle as the notation for the gradient. It's simply a vector whose components are the partial derivatives of the function. Okay, so in a way you can think of the differential as a way to package partial derivatives together into some weird object. Well, the gradient is also a way to package partials together. So we'll see on Thursday what it's good for, but some of the problems on the p-set use it. So